This video is going to cover herd immunity, which is a term that applies to both humans and animals, and you might have heard it during the COVID pandemic. And it's basically the indirect protection in a population of disease transmission by virtue of having some people immunized rather than everyone immunized. So this is just the population I'm going to use to kind of outline how herd immunity works at like a conceptual level, and then afterwards I'm going to talk about some of the like math to actually quantify herd immunity. People that are colored black are susceptible to be diseased, and this is just an infectious disease we're talking about. If you're outlined in green, you're vaccinated. Colored red means infected, and yellow means recovered. Like an infectious disease where if you're recovered, you're no longer contagious, is basically the assumption I'm making. And R naught, the equation for that is CPD. That's the rate of contacts, the probability of transmission per contact, and the duration of infectiousness. And that comes to 2 in this like hypothetical disease, and that pretty much means anyone who's diseased is expected to, on average, infect 2 other people. So with all of that in mind, let's watch an example of how this might play out. This one infected individual would infect 2 other people, who would in turn infect 2 other people, and you can see how this starts to spread really quickly. And each of these red people can only go to the people who are colored black. The yellow people can't be infected by them because they're basically immune in the natural way, not the like vaccine way, but the way where like you've recovered from the disease. So a consequence of that is that you'll see here now that we're starting to run out of susceptible people, where this newly infected person has some people that are available to infect. Same here, but these 2 circled ones have been kind of boxed in. This is obviously just like an example. People in reality move around in space, but I guess this is like an analogy for the circle of people you interact with in your daily life. So as this continues, it starts to basically infect everyone really quickly, and just to kind of illustrate what happened, where we started to run into these situations where these people got boxed in. That kind of helps to explain why. This is from another video I'm planning to do later on. That shows just kind of how epidemics progress sometimes, where the proportion of people that are infected rises really rapidly as just that there's so many susceptible people available, and it's just the R naught is kind of at its full capacity. If it's an R naught of 2, everyone's going to infect 2 other people basically. It starts to slow down when, even though the disease has an R naught of 2, the amount of susceptible people to be infected starts to disappear, and then this effective R naught that's like a function of the original R naught and the proportion susceptible causes this basically to slowly die out, instead of it just being this like uniform curve that's like symmetrical. So to illustrate herd immunity, I'm going to go through that same example, but we have 25% vaccination. So there's 40 people here in total, and 10 of them are vaccinated. And again, obviously, this is way more like complex than, because real people aren't laid out in a grid like this, but this just kind of illustrates an analogy for how it works. So this one infected person goes on to infect 2 people, and they go on to infect 2 people. But already, this person could only infect 1. They were basically surrounded by immunized people, or vaccinated people, I should say. So you're already seeing the effects of herd immunity. 2 other people. What I've done here is just to show that the vaccine is not always like 100% effective. The video I posted yesterday is all about that, and that can maybe be because they were already sick before they got the vaccine, or the vaccine was administered ineffectively, or something, or it's just not, the vaccine just doesn't have 100% efficacy or something like that. But the consequences of that, and why I put it in the example, is that this person, even though they got infected, the immunization might allow them to not manifest like symptoms that make them contagious. This would just show in this example how the vaccine still kind of had an effect, in the sense that the person got sick, but they weren't able to infect others, and there was still some protection at the population level. But yeah, still just continuing to progress. This other side continues to get decimated. These 2 Vaccinated people weren't enough to protect everyone, but it probably slowed it down a little. But you have this whole group of people here that were basically protected by virtue of other people's vaccination. And yeah, it's more complex in the real world, but this is just kind of an analogy for what it looks like. In order to quantify it, you need to have these like three distinct groups of people. So, population one is this population where the vaccine is readily available, and population two is one where it isn't. The difference between the two could be time, like the no vaccine population could be from a time before the vaccine was available, or like population one could be in a more developed region where the vaccine is readily available, and population two could be a developing country that doesn't have it yet. So the risk in the vaccinated, there's in this side, there's the vaccinated is just those people outlined in green. There's that one person who's infected and vaccinated, and there's one, two, three, four. There's six vaccinated people in total. So the risk in the vaccinated is 1/6. Unvaccinated, that's 1, 2, 3, 4, 5 of 6, 7, 8, 5 of 8. And in this other whole population, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 13, 14. So using these different risks, and that's the last time I'm going to be counting them all. From now, I'm just going to like reference the risk. So the direct effect of the vaccine is comparing the risk in the vaccinated to the risk in the unvaccinated in this population. So the direct effect would be risk in the vaccinated to risk in the unvaccinated. So 1/6 over 5/8. It comes out to 0.27, and to get a more interpretable effect, 1 minus that, you get a 73% direct effectiveness. The indirect effects of the vaccine, you compare the risk among the unvaccinated in population 1 to the unvaccinated in population 2, which is everyone because there's no vaccine in that population. So basically, you're looking at the risk in the unvaccinated here. So you would have 5/8, and then over the risk in this population, so over 10/14, 0.875, 1 minus that. So there's some effect, like this 13% effectiveness that these unvaccinated people get just by virtue of being in the population where the vaccine is available and other people around them have the vaccine. And just some other ones are the total vaccine effect. That's comparing the risk in the vaccinated here to this population here. So 1/6 risk in the vaccinated to 10/14 the risk in this population. We get 0.23, and it comes out to an effectiveness of 77%. So that's a bit more than the one before that had 73%. So that's just showing. Yeah, that's just showing that the total effect, so the direct and indirect collectively, speaks to a bit more effectiveness even than just comparing within this population. The overall effect is comparing population 1 to population 2, so collapsing everyone in this group into 1. The 5 and the 1 go into 6, and the 6 and the 8 become 14. So the risk in this whole population to the risk in this whole population, you get this total effect of 0.6, so 40% effective.